This is a message to recovering stroke patients, physical therapists, and research institutions. We have developed a walking rehabilitation device that is capable of assisting recovering stroke patients in the later stages of physical therapy. Our physical therapy walking aid is intended to specifically target the weakened side post-stroke. Stroke is one of the leading causes of adult disability in the United States, leaving an estimated 7 million stroke survivors. In addition, only 61% of stroke patients receive both physical therapy and occupational therapy services in the acute hospital setting, with 35% patients receiving no physical therapy at all within the first 3 months post-stroke. The recovery of walking ability post-stroke is also a key functional goal in rehabilitation, and thankfully, approximately 65% of hospitalized stroke survivors with motor deficits in the leg were able to recover some degree of motor recovery after physical therapy. And lastly, research has shown that Medicare patients who received only 75 minutes or more of physical therapy while in the hospital reduced their risk of readmission by 14%. Physical therapy treatment can help restore movement, walking ability, improve recovery, and ultimately guide the patient towards independence and increased quality of life. For the device to function properly, the following product design specifications were considered. It must work on both linoleum and carpet, which are the most common types of flooring in physical therapy offices. It must alert the therapist if the user is detected to be falling for safety reasons. It must be able to walk itself a distance of at least 1 meter with no external assistance per project requirements. And it must also be able to provide power assistance to the user within 1 second of user input. The following constraints must also be considered. 1. The device must fit in a 3x3 by 6 feet box so that it can fit through doorways. And lastly, it must weigh less than 50 pounds for ease of use and transport by the therapist.
The device features 3 fixed support legs and a frame that allows the user to stand to the side of it and be strapped in for support at both the leg and arm. The casters allow the device to move forward and backward, while the angled leg with the tennis ball allows the user to lean on the device for support. The leg is fixed to the device through the use of a knee brace, which is strapped through a pressure-sensing leg board mechanism. By allowing the device to be used in conjunction with the knee brace, the user's leg will maintain proper alignment and range of motion set by the physical therapist, while also remaining comfortable for the user. The leg pad mechanism is fixed to a mechanical linkage powered by a stepper motor. When the sensors detect the user is trying to walk, the motor will operate and provide a power assist to the user's leg. This function is similar to how power assisting motor operates with an e-bike. The linkage utilized was designed using MotionGen Pro. The path of the linkage was set to mimic the ideal gait of a human leg. The linkage also needed to be compact so it would not get in the way of the user and operate in a way that would allow the foot to maintain appropriate contact with the floor. The linkage is constructed using plasma cut aluminum plating and spaced using bolts with washers, lock nuts, and Delrin tubing to ensure low friction throughout. The output link that connects to the user's leg is driven by an input crank link made of 3D printed Nylon X filament. The 2 input links rotate about a shaft printed with the same material. The links are force-fitted to the shaft through the custom designed keyhole and screwed together using machine screws. In the middle of the shaft is a timing belt pulley fixed to the shaft using a 3D printed key and grub screws. The timing belt maintains a 1:1 ratio as the other pulley is connected to a 20:1 planetary gearbox fixed to the stepper motor. This motor and gearbox combination provides sufficient torque on its own to drive the linkage, overcome its internal friction, and lift the user's leg. The motor and electronics are powered by a 36-volt 10 amp hour e-bike battery to provide enough power for the device to run continuously for at least 1 hour. This battery is directly connected to the stepper motor driver, which is controlled by an Arduino Mega microcontroller. The Arduino is powered by a 9-volt battery and detects input from the pressure sensors as well as a rotary encoder fixed to the input pulley. The Arduino uses the input from these to calculate what the motor output should be and will make the motor run accordingly. The Arduino will also set an LCD to display the distance traveled as well as the average speed during the session. Test 1. Light carpet test. Since the device must be capable of moving smoothly in a doctor's office environment, the device has been tested to move forward and backward on both bare flooring and light carpeting. Test 2. Walk 1 meter. The walker must also be able to walk on its own for at least 1 meter. Therefore, a plastic testing foot was fixed to the bottom of the linkage, allowing the device to propel itself forward. Test 3. Fall detection. To test for safety in case of a fall, the accelerometer detects if the device is moving left or right in a falling motion, which will trigger a buzzer.
The following footage demonstrates the function of the prototype. The user is strapped into the knee brace with the help of the physical therapist at the thigh and at the arm. After being strapped in tight, the device is switched on by the physical therapist, providing power to the electronics. Note, the same switch can be used by the physical therapist in case the device needs to be immediately shut down. Once switched on and the physical therapist has set the level of assist, the device awaits input from the user. When the user attempts to lift their leg, the sensors detect input from the user and the motor will run to provide assistance. Now running smoothly, the user walks with assistance from the device, while the therapist can read data on how much force the user is applying to their leg to move forward. After finishing a session, the device can be turned off and the user is unstrapped from the device. In conclusion, we have completed a working prototype of this device that complies with our specifications. If given longer time and a greater budget, many of the materials and designs can be further improved in the future. Hopefully, this device and others like it can one day make lives easier for those recovering from a stroke. Thank you for watching!